Welcome to the subject Electromagnetic Waves and Transmission Lines. In this session, we shall be discussing the topics electric flux density, Gauss law and its associated applications. So let us start with flux density. So before going to understand what is flux density, first we should understand what is electric flux. Electric flux is a visual representation of electric lines of force. If you have a charge Q, a positive charge Q, immediately what will happen? It is surrounded by its own field, which we say the electric field of that electric charge Q. Well, you cannot visually see that electric field, but you can experience it by placing another electric charge. If you place another negative charge, there is force of attraction. If you place a positive charge, there is a force of repulsion. So electric field cannot be visually seen, but it can be experienced by placing another electric charge. Now you have electric lines of force diverging in all the directions. If it is a positive charge, the lines of force go outside. Bunch of such electric lines of force or group of such electric lines of force will constitute electric flux, and its symbol is psi, a Greek alphabet to indicate electric flux. Unit is same as unit of electric charge, coulomb. So now what is electric flux density? Electric lines of force crossing a unit surface area such that this surface area should be held in the normal direction to the flow of flux. Well, you know, you have tangential direction and normal direction. Normal means which is perpendicular to the direction of flow of flux. So for that we indicate a bar, a unit vector a bar to indicate the direction along normal direction. So we use a bar n. That is what you find here. So the direction of electric flux is normal. Why? Because what is electric flux density? The amount of electric flux crossing a unit surface area normally. So we find here, this electric flux is crossing this unit surface area in the normal direction. Of course, here we say normal because the flux is perpendicular to this differential surface area. If we compare this as a sphere, then this is nothing but radial. That is called radius. This is called radius, and this direction is called radial direction. So contextually, you can say it as normal direction, normal to the surface. How much flux is crossing a unit surface area in normal direction. So in this context, it is called normal direction. Inside the sphere, this is called radius. So we say this also has radial direction. We can say a bar r. That is the reason I have written here a bar r, a bar n. In the definition of flux density, mathematical definition, I have written a bar n. In the mathematical expression, I have written a bar r, radial direction, because both happen to be same. Now as I told you, what is electric flux density? The differential flux crossing a differential surface area, dψ by ds. Flux per unit surface area or differential flux per differential surface area. This tells you the magnitude, this gives you the direction, because flux density is a vector quantity. And what will be the units? Amount of flux, coulomb per unit area, meter square, coulomb per meter square. This is the unit of flux density. Now, if you want to use the mathematical framework, that is to calculate the flux density, we use the expression, this one. Well, we know electric field expression. If you recollect, so remember, what is the expression? E bar is Q by 4 pi epsilon naught R square AR bar. This was the expression for electric field. Now we are working with D bar. What is the relationship between D bar and E bar? You know, there is one constitutive relationship, that is D bar equal to epsilon naught E bar. That means if you multiply electric field with epsilon naught, you will get D bar. So do that. So you take E bar 4 pi epsilon R square AR. This is E bar. Multiply with epsilon naught. So multiply with epsilon naught. Epsilon naught cancels. What remains is Q by 4 pi R square AR. The same thing you find here, Q by 4 pi R square AR. This tells you the magnitude, magnitude of the flux density. This tells you the direction. So how do you get this direction from? From the electric field A bar, which means that the electric field E bar and electric flux density D bar will have the same direction. Next, electric flux density and electric field are related to each other by the electric permittivity of the medium. This is another relation you can make out. So this is about electric flux density. Next, similar to Coulomb's law, we have something called as Gauss law. Coulomb's law deals with the electric force resulting between electric charges. That deals with force and electric charge. There is another law which deals with electric charge and electric flux. That is known as Gauss law. So next our discussion will be focused on Gauss law. So what is Gauss law? In a simple form, the electric flux passing through a closed surface is equal to the charge enclosed. To understand it in simple manner, the electric flux is equal to the electric charge. Electric flux is psi, electric charge is Q. Psi equal to Q. Straight away you can say psi equal to Q. This is Gauss law. To be more comprehensive, the electric flux passing through a closed surface is equal to the charge that is enclosed. I write here ENC, means charge enclosed. Suppose there is a closed surface. The closed surface need not be a perfect circle. It can be of any geometry. It can be of irregular shape. So the closed surface need not be a perfect circle. It need not be a regular geometry. It can be of any irregular shape. But the surface should be closed. So charge enclosed will give rise to flux. That is the meaning of this. Electric flux passing through a closed surface is equal to the total charge enclosed. There can be some positive charge. There can be some negative charge. Plus 5 coulombs, minus 3 coulombs. What is the net total flux? It is plus 2 coulombs. So accordingly you will get the flux. Now let us try to decode the Gauss law further. Observe the three diagrams carefully. When I say electric charge, it can be a point charge, it can be a line charge, it can be a surface charge, it can be a volume charge. We have discussed this topic in charge configurations. Charge configuration means how an electric charge is spread or distributed. If the entire charge is located on a point, we say point charge. If the charge is spread on a line geometry, we say line charge. Like that, surface charge, volume charge. So observe these three diagrams carefully. In the first case, I have taken a dot, means point charge. What is the amount of charge? 5 coulombs. What Gauss law says? Psi equal to Q. Whatever charge is there, you will get equivalent flux. So what is flux here? 5 coulombs, because charge is 5, flux is 5. Now instead of point charge, I have taken here line charge. The same 5 coulombs of charge is now spread on a line geometry. Now what Gauss law says? Psi equal to Q. Whether it is point charge or line charge or surface charge, doesn't matter. Whether it is surface charge or volume charge, it doesn't matter. Flux is equal to charge. So how much charge is there? 5 coulombs. So psi will be 5 coulombs. Now in the third diagram, in the first diagram you have point charge at the center of the closed surface. In the third diagram, you have this point charge on the top of the closed surface. Means the location has changed, but still the flux is 5 coulombs because charge is 5 coulombs. So what you can infer from these three diagrams? If you change the type of charge configuration, the flux has not changed. If you change the position of the charge, flux has not changed. So flux is independent of the type of the charge configuration. Flux is independent of the position of the charge inside the closed surface. Flux is dependent only on the amount of charge that is in the closed surface. This is how to interpret Gauss law in a more detailed way. Next, we shall go for the applications of this Gauss law. typical applications we go for. Then we go for some special applications. By default, you have point charge. So what is the expression? In the previous slide, I have shown you. The expression is Q by 4 pi r square AR. By default, whenever we write this expression, that is meant for point charge. So the same expression you have here, Q by 4 pi r square AR. This is for point charge. If it is for infinite line charge, let us say the charge is distributed on a line geometry, and the length of the line happens to be infinite. Infinite means not really absolutely infinite. The length of the line is too big. So we say it as infinite line charge. In such a case, what is the flux density? Rho L by 2 pi r. Because the charge is spread on a line. Then you measure electric field surrounding the line. This is called circumference, 2 pi r. Direction is same, radial direction, like this. This is called radial direction. And rho means electric charge density. L means line charge density, because the charge is spread on the line. So we have taken here rho L. Now what is the difference that you notice from point charge and infinite line charge? The difference is, major difference I am speaking. Here you have r square, here you have r. Means with little incremental in distance, there is a rapid decay of electric flux density, because it is r square, 1 by r square, reciprocal, denominator is there. Whereas here, it is not r square, it is r. With a little increment in distance, you have gradual decrement in flux density. That means flux density do not rapidly change with distance. It will gradually change. In both cases, flux density falls, means it decreases with increase in distance. But here it happens rapidly, here it happens gradually. Just here you have r, here you have r square. Next, infinite sheet of charge. Let us say the charge is spread on a sheet of charge such that the size of the sheet will have area. Size means area of the sheet is too big. If the size of the sheet means if the area of the sheet on which the charge is deposited, if it is too big in relation or with respect to the distance at which you are measuring the charge, then that is treated as infinite sheet of charge. Such a case you have rho s by 2. Here you have r square, here you have r, here there is no r. R is the distance between the point P at which you are measuring the flux density and the charge due to which you are measuring the flux density. There is no r here, which means the flux density that is measured in this case is not dependent on the distance. For infinite sheet of charge, it is independent of distance. Then what we have? Rho s here. Rho means charge density. It is sheet of charge. So we have rho s means surface charge density. Next you have some special scenarios. The first scenario is spherical shell of charge. Shell means which is empty inside. That we say shell. Empty in the sense, in this case empty means there is no charge inside the shell. It is there outside. So that is the reason, if you observe carefully, there is a sphere and charge is deposited on the surface. Inside there is no charge. So we say it has a shell. It is in spherical shape. So we say spherical shell of charge, means electric charge is there. Now here we have three scenarios. First, try to understand the geometry. There is a sphere which is a dark line and there is another sphere which is dotted line. Dotted line indicates imagination and dark line indicates which is actually there. So both are spheres. This is actual sphere, physical sphere, physically you can see it. And this dotted line indicates imaginary sphere, which is also referred as Gaussian sphere. Now, if you take a point P, let us say point P, outside the physical sphere, take a point P on the physical sphere, take a point P inside the physical sphere. If you take a point P inside the physical sphere, then you get a small imaginary sphere. Its radius is less than the physical radius. That is called r less than a. Now, if you take a point P on the physical sphere, then radius of Gaussian sphere or radius of physical sphere are same. R is equal to a. This is the case. If you take a point P outside the physical sphere, then this is the radius, R is greater than A. This is a case. Now you have three regions wherein you want to find out the expressions for the variables about the flux density. In the first case, R greater than A, d bar is Q by 4 pi R square, AR. The basic expression which you have been seeing from the previous definitions. There is no change. Now if R equal to A, what will happen? In place of R, substitute A. Because R equal to A, so substitute A. Then what you get here? Q by 4 pi A square. It's simple and straightforward. Next, for R less than A, the electric flux density ceases to exist. It does not exist. 0 means it does not exist. There is no flux density that can be measured. Why it is the case? Because if we take a point P inside physical sphere, then this is the radius and this is the Gaussian sphere. What Gauss says? If you have any electric charge within a closed surface, then flux will come out of the closed surface. Now in this Gaussian sphere, is there any charge inside? There is no charge inside. So flux will be 0, flux density will be 0. Now if you try to make a graphical sketch out of these three scenarios, how it would look like? So on the x-axis you have distance, R in meters, and in the y-axis you have electric flux density. We are dealing with its magnitude, the strength of magnetic flux density, electric flux density. Now if you observe carefully, for R less than A, this is R equal to A, this point is R equal to A. So obviously this will be R greater than A, this will be R less than A. For R less than A, the flux density is 0. So you don't find any flux density here, it is 0 here. Now at R equal to A, suddenly the flux density rises to Q by 4 pi A square. So it suddenly rises to Q by 4 pi A square. Then for R greater than A, the flux density is inversely proportional to R square. Means with increase in distance, the flux density falls. Not linearly, non-linearly, because it is not R, it is R square. So for R greater than A, the flux density decays with R. So that's what we find here. It is decreasing non-linearly with increase in distance for R greater than A. So this is the physical analogy. These are the mathematical expressions and interpretations. This is the graphical way of understanding this application of Gauss law. Next we have another scenario. Which is termed as uniformly charged sphere. Previously I told spherical shell of charge. Shell means there is no charge inside, charge is there outside. Here I am saying uniformly charged sphere, means sphere is charged. So you have charge inside the sphere. Previous case, charge is there outside the sphere, on the surface of the sphere. Now inside the sphere, the charge is there. That too uniformly distributed, charge is distributed. So we say this as uniformly charged sphere. Same process we adopt here. This dotted sphere is called Gaussian sphere, which is imaginary sphere. Its radius is R. This dark sphere is known as physical sphere or actual sphere, whose radius is A. Same, R A. Now, if R is greater than A, what is the flux density? Because charge is spread in the volume of the sphere. This is called surface. Inside the region is called, geometrically we call it as volume. So charge is there in the volume of sphere. So we take rho V. Rho means charge density, V means volume charge density, because it is charge is there in the volume of the sphere, rho V. That's why we find rho V in all the expressions. Next, direction is same, radial direction. Flux density is same, having the same direction as electric field, AR. Next, R stands for radius, or the distance between the charge and the point P at which you are measuring the flux density. Now in the first case, R greater than A, what do you have here? Rho V, charge density, which is constant. A is the radius of the physical sphere, actual sphere. It will not change. It is constant. 3 is constant. So what is there here? Flux density is inversely proportional to R square. Means R is the distance at which you are measuring flux density. As R increases, flux density falls for R greater than A. So for R greater than A, flux density, the magnitude of flux density falls non-linearly, because it is not R, If it is R, you get like this, linearly falling. It is R square, so it falls rapidly. That's why you get like this. Next, second case, if R equal to A, just in place of R, substitute A. What do you get here? You get A square, rho V A cube by 3. In place of R, substitute A, 3A square. A square, this cancels. What remains? Rho V A by 3. Rho V A by 3. The same thing you have here. Now, for R equal to A, rho V is constant, A physical radius, it is constant, 3 is constant. So, at R equal to A, you get a value of flux density which is equal to rho V A by 3. So, this is rho V A by 3, this point. Next, for R less than A, this is R equal to A, this region is called R less than A. For R less than A, what do you find here? Rho V constant, 3 constant. So, flux density is directly proportional to R. D bar is directly proportional to R. Here it is there in the denominator, here R is there in the numerator. Means as distance increases, as R increases, D increases. So, that's why you find that too linear, because it is not R square or R cube, it is R. So, it is a linear relationship. So, that's the reason flux density is linearly increasing with increase in distance for R less than A. This is R less than A region. Now, why this is happening like this? For R less than A, why the flux density is increasing with R? The reason is R less than A means take a point within the sphere. So, this is R. If you take a point P inside the sphere, you get small Gaussian sphere. So, this small Gaussian sphere will enclose a little amount of charge. But if you take a point here, you get a big Gaussian sphere which encloses more electric charge. As per Gauss law, if it encloses more charge, you get more flux and more flux density. So, that's the reason for R less than A, as you increase R value, the flux density value is increasing. But if you take a point here or here, the same thing, it's the same thing. R is greater than A. As you increase R value, the sphere is becoming bigger and bigger. Gaussian sphere is becoming bigger and bigger. But the amount of charge the spheres are enclosing, they do not increase. Only the size of the Gaussian sphere is increasing. The amount of charge that is being enclosed, it is not increasing. So, there is no increase in flux density with increase in distance. Instead, you have decrease in flux density, strength of the flux density, because you are going farther and farther. So, the strength of flux density decreases. That is the reason you find this behavior. Linearly increasing, non-linearly decaying. This is a linear part, this is non-linear part. This is a linear increase, this is non-linear decrease. And this is constant. At R equal to A, this is constant. So, these are the typical case studies or applications of the Gauss law. With this, we end our discussion of electric flux density, Gauss law and its associated applications.